Okay, gang, welcome back. Guess what today is? Y'all have been begging for this, so here it is. Slope and deflection. In the last video, we talked about beams and the endpoints on how they were constrained and what the slope and deflection was. We knew that, at a pin connection, the deflection was 0. We're going to use those constraints, those end conditions, to try and solve this problem today, okay? So this is a little more complicated thing here for slope and deflection, okay? So one of the things that you need to know is this. Okay, we do have a new equation, and that equation goes like this. How does it go? You know what? We're going to have to integrate twice. Okay, equals the moment divided by E times I. Okay. So what this is saying here is this, okay? Here's what we know. If you take a beam and you integrate it, right, what do we get next on the next curve down? Remember, we get the V curve or the shear curve. If we integrate the shear, boom, we will get a moment diagram. We will get the M curve. So if we integrate that again, we'll get the slope. And if we integrate it one more time, we'll get the deflection, okay? So it's like 4 integrations to get there, right? And so this is kind of in the middle, okay? This is looking at the moment. So we need the moment equation here, okay? So we're gonna do it a different way. We're not gonna do this shear moment diagram to do this. We're gonna just write some equations. But we need this moment function, okay? So we need the moment function of the beam. And then this tells us we need to integrate that twice, okay? And it makes kind of sense, doesn't it? Because if you take this and you integrate it, you just get this, right? And do y'all remember from back in calculus? Do you remember back in calculus? If you had like a curve, like here's a parabolic curve, and you take the derivative of the function at any point, what do you get? Remember, you got the slope of that point. So the derivative is slope. We'll just call that theta. So again, we had the moment function here. We integrate that, we get the slope, and then if you integrate that one more time, you get y, okay? You get displacement. So those are the two things that we're going to look at, right? Is slope and displacement. Okay, I'll leave those over there, okay? So that's kind of what we're doing. So here's the equation we're going to use today, okay? So right off the bat, the thing that we need to do is we need to find, and why, let me tell you one more thing, and why is there an EI in here, right? Because we are talking about slope. I mean, this beam is going to deflect to, I don't know, something like that, right? There's the deflection of that beam. Well, what factors play into like the bendiness of a beam, the bendiness of a material? Well, it's modular elasticity, right? Is it made out of steel or is it made out of rubber? One's not very bendy, one's real bendy, right? Bendy's not a word, is it? But anyway. And then what does this guy do? The area moment of inertia, right? That's why a diving board, which is just a flat plank, is very flexible. But an I-beam is not because of its moment of inertia. So if we know about the material properties and we know about the beam's cross-section, then that would tell us how bendy it is so that we can determine what the slope and the displacement is going to be. So that's why we need to know E and I in this equation, okay? So we're going to use this. So the first thing we need to do is we've got to find out what is the moment. We've got to write an equation for the moment with respect to x for this beam. Now we're going to write 2 equations for this, okay? We're going to write one in between A and C. There's one moment equation. We'll call this piece number 1, and then between C and B is another one. So that's piece number 2, okay? So let's see if we can remember how to write those equations. Oh, here we go. Step 1. What's step 1? Step 1 is to just like always, find global equilibrium. God, we're so good at that. Here we go. All right, what do you think we do? Let's take the moment at A. Okay. So if we take the moment at A, let's see what we have. We have P, which rotates us That's negative, right? So negative P times how far away? Let's just call it L over 4, okay? And then what else do we have? Oh, we have a, over here, we have maybe a BY. Over here's our AY. Okay? So, and then we have minus B, or that's actually plus, isn't it? Plus BY times, well, 1/4 plus 3/4 is just plain old L, isn't it? Okay? And so from that, let's see, we have, what do we have here? BY is equal to 1/4 PL, right? Move this to the other side and then divide the whole thing by L. So there it is, right? So BY equals 1/4 P. And AY must equal, well, there's a whole P going down, so this guy must be 3/4 P. Okay? All right, there you go. That's step 1, global equilibrium. We can do that, can't we? Okay? All right, I'm going to erase this. There's a lot of stuff going on here. Okay? Guys, this is not an easy problem. It goes on and on and on. It's going to take us forever to do this. So I hope you have a snack. If you don't, push pause and go get you some popcorn and come back, because it's going to be, you know, a long time here. But we'll get there to the end. Okay. Step 2. What's step 2? Step 2. Okay. We need to cut through the beam, let's just say through the section of interest, and then from that we can find equation for V and an equation for M, okay? So we have 2 sections from A to C, right? And then from C to B, we have section 1 and section 2. So let's start with section 1. And what we're going to do, let me get another little pen over here, is we're just going to cut right through here. Squiggle, right? At a distance of, that distance is X, from there to squiggle to there, okay? So we're going to solve that by doing this little free body diagram here. Okay? This is just like we know how to do this, right? We cut the beam, so what do we have to have? You must have a M and V. Right, here's your N, here's your V, and here's your M. Okay, and then over here is my 3/4 P. Okay, and this guy is not on this free body. He's like over here somewhere, right? So it's going to be pretty simple, right? So V is equal to, right? And if you don't get this, the sum of the forces in the Y equals 0 equals what? Minus V plus 3/4 P. So therefore, move that to the other side, V equals 3/4 P, right? Okay, so there's your equation for V. Okay, let's get the equation for M now. Let's take the moment here about the end of the beam, okay? Again, this is our positive. So summing the moments, let's say at X, right? This distance here is X, okay? So summing the moments at X equals 0 equals what do we have? We knocked out N and V, but we have this moment, which I drew as positive. So M, and then this guy's rotating me negative, minus 3/4 P times how far away? Times X, okay? So M is equal to 3/4 P times X. And there it is. Okay? There's an equation for moment. For section 1, right? That's the moment for section 1. Okay? So we needed that equation. So let's come over here. Let's do section 2. Okay? Oh, it's a big beam now. Okay, so now I'm cutting it through here somewhere. I don't know, right? And so now this is X. Okay? This is my new X for section 2. I cut through section 2 to find an equation for the moment in there. So, and I have this. Over here we have, again, 3/4 P. And here's that P force, P. And then what? We have this, an N, a V, and an M. And this distance is X. Okay? So same thing we did here, let's do it one more time. Okay, we got an equation for V, and we got an equation for M. And that's the one I'm after is M because I need that for right there. Okay? So let's find that again. Here we go. So sum of the forces in the Y equals 0 equals minus V minus P plus 3/4 P. That's this guy. That's it, isn't it? So V is equal to 3/4 P minus P. Okay? Oh, and 3/4 P minus a whole P leaves you with minus 1/4 P. Okay? So there's an equation for V. And M, again, here's our thing. Sum of the moments about point X. Okay, here we go. So we got an M, which is positive. So M. The P, we're taking the moment here, right? The P rotates me that way, which is a positive, isn't it? So plus P times how far away? Let's see. How far is that? Well, we know that this over here is what? 1/4 L, right? So then this distance here must be X minus, let's just call it L over 4, right? So that's what that distance there is, okay? So P times X minus L over 4, you know, force times distance, right? And then this guy rotates me, he rotates me negative, so minus 3/4 P, 3/4 P times how far away? Times X away, okay? Can we simplify that some? Okay, so M plus PX minus PL over 4, right, minus 3/4 PX. So let's make that, the PX's go together, don't they? That and that go together. So I wind up with this. M is equal to, because all that was equal to 0, right? So I'll move all that junk over there to the other side, okay? And so I get a PX, so that's going to be minus 1/4 P times X plus PL over 4. And that's it, okay? So there, boom, is the moment equation for section 2, okay? That's pretty easy to follow in it. That's something we've been doing the whole time, okay? So that part shouldn't be too confusing. I'm going to write those two equations over here, and then I can kind of erase that and we'll reuse that. And so number 1 moment equation is M equals, erase that. Okay, let's erase all this business. And I don't want these V equations. I mean, they're handy, but I don't need them for this. 3/4 P times X. Okay, there's one of my equations. And number 2 was down there, M equals 1/4 P times X plus P times L over 4. Okay, so there's my second moment equation for section 1, section 2. Okay, did I write that down right? Yes, and yes. Let's erase all this. Okay. Okay. Okay, the next thing we're going to do, we did this, we're all good on step 2. Step 3, identify boundary conditions. Okay? And we've got a few of those for this problem. These are important too. We're going to need this. Because what we're going to be working for, we're going to have 4 unknowns We need 4 equations to solve for these unknowns, so we're going to need all the help we can get. So the boundary conditions for this beam. What do we know about that beam? Well, here's what we know, okay? When x is equal to 0, okay? So when x is equal to 0 on this thing, what do we know about the deflection at point A? What do we know about the deflection at point A? Well, I'll tell you what we know. y1 is equal to 0, isn't it? The deflection for segment 1 at when x equals 0 is 0. It's 0 in the y direction, right? Remember, we're either talking about slope or deflection. So those are the 2 things that we're getting boundary conditions for, is slope and deflection, okay? So there's one of them, okay? We can call that number 1 boundary condition. Number 2 boundary condition. Okay, what would number 2 boundary condition be? I don't know. How about when x is equal to L, what's going on? So now we're at L, we're all the way over here. Well, y2 is equal to 0. Okay. Let's see, what else do we know? Here's what we know. When x is equal to 1/4 L, okay? Number 3. When x is equal to, let's just call it L over 4, right? Instead of 1/4 L, let's call it L over 4, right? What do we know? There's 2 things, right? Here's number 3, here's number 4. X equals L over 4. So number 1, that's an equal. That didn't look like an equal, does it? Tall people writing on the bottom of the board. Not good. Okay. So let's do slope first. What do we know about the slope when x equals L over 4? So at this point, let's put a dot right there. Okay, here's the slope. Ba-ba, right like that, right? So what do we know about the slope? What do we know about the slope for section 1? So you're 1 molecule on that side of the point C. You're in section 1. You're 1 molecule that side. Would you agree that the slope is the same as 1 molecule that side of point C? So what we're saying is that the slope, theta 1, is equal to theta 2. Do you agree with that? So the slope for section 1 is equal to the slope for section 2 right at that point. That's a little bit hard to get your brain around, but that's what's going on there, okay? And the same thing for this one. When at L over 4, what is the displacement? What is y right here? Do you agree that in this section, 1 molecule this way, it's y1, 1 molecule that way, it's y2. And right at that point, y1 is equal to y2. The displacement is the same whether you're in that segment or that segment. In other words, the function is continuous right there. There's not like some kind of whoop, some kind of like discontinuity there, like you remember in our diagrams when we had like a jump there, right? So it's continuous, so the slope on this side is the same as the slope on that side. The displacement is the same there as it is there. All right? So if you followed me so far, we're doing really good. We've got our moment equations, we've got our boundary conditions done. We're ready to start writing our equations, which is this guy here, okay? So we're going to do this for section 1 and section 2. Let's see if we can write these equations, okay? And they're going to go like this. I'm going to move this EI to that side for a minute, okay? So I get d squared y over dx squared times EI is equal to, okay, the moment equation. Let's do, this is for section 1, okay? This moment equation here, 3/4 px. 3/4 px, okay? So here we go. This is the moment, so we're going to integrate it. Here we go. We get this. We get dy dx times EI is equal to constant 3/4 p, and then this turns into x squared over 2. Oh, let's make that into an 8, okay? There you go. Now it's integrated one time. Now, one other thing that we can do is this. dy over dx, what did we just say that was really and truly? It's the slope, right? So we could rewrite that guy, or erase that. Let's replace that with theta 1, because we are doing section 1, right? Oh, we integrated and we didn't do one thing. What is that? Plus, there's a constant on there now, isn't there? That's the unknown that we're trying to solve for, these constants, okay? That's the hard part. Okay, so let's integrate that again. So I integrate theta and I get y times EI, constant, is equal to, okay, here we go, integrating. What are we going to get here? I don't know. Oh, what is that going to be? 3, let's see, that's going to be a cube, right? 3/8 p x cubed over 3 plus c1x plus c2, right? So that equals y is equal to 1 over EI times, times what? Times 3 over 24 px cubed plus c1x plus c2. Okay? So that's an equation right there. We'll put a little star by him. And here's an equation for theta. I guess we could say that theta 1 is equal to 1 over EI times 3/8 px squared plus c1. Okay. So there's our two equations right there for slope. That's actually deflection. For deflection and slope for section 1 of the beam. Okay, so those are important. Let's put a box around those guys. Those are important. We're going to have to come back to those fellas. Okay. Let's do the exact same thing we did, but now let's do it for equation number, or section number 2. Okay. So what do we get for doing that? Okay, we'll put a little divide down here. Okay. And so here we are. Let's see. Oh, you know what? We could do step 4 over here, couldn't we? Sorry. Step 4. Step 4 is substitute. Substitute. Okay, there you go. In moment and integrate twice. Oh my goodness. Okay. So here we go. The next one's going to be d squared y over dx EI equals, okay, our moment. And our moment this time is this. So minus 1/4 px plus PL over 4, okay? And so we integrate that and we get this. We get theta 2. This was theta 1. This was y1, okay? Theta 2 is equal to 1 over EI times, okay, here we go, we're integrating, negative 1/4 px squared over 2, so turn that into an 8, okay? Plus, what is that going to turn into? That's just a constant, PL over 4 times x plus c constant. We already had a 1 and a 2, so that makes that guy constant number 3. Okay. Can we combine any of those? I don't think so. That's about it, isn't it? Okay. Let me erase these guys. We're going to need all the room in the world over here. There's theta and there's y. Okay. So I don't think I can get any more simple than that. Okay. So let's integrate that again. And we integrate that again, we get y is equal to 1 over EI times, oh lordy, okay, 1 over cubed, right? Let's do this, 1/8 px cubed over 3, okay, plus pl over 4 times x squared over 2 plus c3x plus c4. Okay? And so y2 is equal to 1 over e times I of, oh my goodness, I forgot my negative, didn't I? Negative 1/24 px cubed plus 1/8 plx squared plus c3x plus c4. Okay, and I can't simplify any more than that. Okay, so there's my equation for theta 2. There, bam, there's my equation for y2. Okay, are you following me so far? So all we're doing is we use that equation to write the slope and deflection for segment 1 and segment 2. Okay, but we have these 4 unknowns, C1, C2, C3, and C4. Okay, so what next? Okay, next we're going to use our boundary conditions and do some substituting. Okay, so the goal at this point, we've got our 4 equations, 1, 2, 3, 4, okay, with the stars by them and the boxes around them. And we got to get rid of C1, C2, C3, and C4. We got to get rid of all those unknowns, okay? So we need some room here, don't we? This problem is going to take up a lot of room, I'm telling you. Okay, so let me erase this. Okay, so I guess if you know how we did those, I don't need this work anymore, so I'm going to erase this. Okay, and erase that. Okay, and I'll erase this. I'm just going to leave our equations that we derived there. Okay. Okay, so, and this is what we want, right? Because we want an equation for the slope and deflection at these points here. Now, if we hadn't written these equations over here, we would have had more than we can solve here. So we had to write these equations to do that. So what we need to do is get rid of these constants, okay? So that's the whole goal here, is to get rid of those constants. Let me write this down here again, and then we can erase that guy, okay? So theta 2 is equal to 1 over EI times minus 1/8 px squared plus plx over 4 plus C3. Okay, so there's that other equation. I just rewrote it so we could get some room here, okay? Make sure I wrote it right. Minus, plus, plus. Okay, that's good. Okay, so the next thing we need to do is we need to talk about substituting and solving here. Let's see if we can do it. All right, we're going to let's take our 2 theta equations. Let's take these 2 guys, okay? And they told us here that what? Theta 1 equals theta 2 when? Well, they didn't tell us. We came up with that, didn't we? Theta 1 equals theta 2 when x equals L over 4. So we could set this bit of this equation and this bit of that equation equal to each other if, for x, we plug in an L over 4. And if we set them equal to each other, do you agree that 1 over e sub I is just going to divide away, right? So what are we going to be left with? We're going to be left with this. 3/8, so I'm doing this guy first, right? P times x squared. But in place of x, I'm going to put an L over 4. L over 4 squared plus C1 is equal to, I'm going over there, minus 1/8 P times L over 4 squared plus PLX PL over 4 times L over 4 plus C3. Okay, that's a C3 PO. Okay, so let's see if we can simplify this a little bit. So what do we wind up with? 3/8 PL squared, and then that's going to be a 16, and 16 times 8 is 128, isn't it? Isn't that right? On 16 times 8, 128. I was right. Okay, so that's going to be 128 PL squared, right? Plus C1 is equal to, oh my gosh, 16 times 8, so minus 1 over 128 PL squared plus, oh my goodness, PL squared times the 16th, right? 1/16. Goodness, PL squared plus C3. Okay, let's see. Do we know 1/16 is how many times divided by 16 equals 8? Okay, so this whole thing over here becomes 7 over 28 over 128 PL squared, right? You turn that into a 128, that turns into an 8, and 8 minus 1 is 7, right? Plus C3, okay, so that's that whole side simplified, is equal to, okay, 3 over 128 PL squared plus C1. And so if I want C1 by himself, I could say down here, I could say C1 is equal to, and I'm going to move that to the other side, right? So let's subtract him over there, so that leaves us with 4 over 128 PL squared plus C3. And 4 over 128 will simplify to what? I don't know. 128 divided by 4. 4? I should know that. 32. How about 1 over 32? All right. So there's a simple expression relating C1 and C3. Okay? Well, that's pretty good. Okay, so what else can we do? You follow that? Let's erase that and get back and try another one. We'll try another substitution here. Okay? Okay, so now we're in what? We're in step 5. Step 5. 5. Substitute. Boundary conditions, and solve for, let's say, constants. Okay, because we need to get those constants out of our equations. Okay. Okay, let's try, I don't know, we haven't tried y, so let's try this for y1. Okay, so when y1 equals 0, oh, wait a second, this is going to be good, isn't it? Then x equals 0. So if we do this equation right here, right, what are we going to get? Well, if y1 is 0, 0, then I over EI times, then I can plug a 0 in for x, right? So that becomes 0, that becomes 0, and I just get C2, right? So move that to the other side. Bloop. What is EI times 0? 0. So right away, C2 equals 0. There's another one. Okay, that was good, wasn't it? Okay, that wasn't too hard. Okay, what else can we do? Okay, let's try this one. When x equals L, y2 equals 0. So here we go over to this guy, and let's use this guy and see what he'll feed us, okay? So that gives us 1 over e times I. Y2 is going to be 0, isn't it? Matter of fact, when I multiply both sides by e times I, again, that's going to go away, isn't it? Okay, that's going to go away. Because if I move that to the other side, it's times 0, it's going to go away. So equals negative 1/24 p. Okay, and instead of x, I'm going to plug in what? Right here. I'm going to plug in this, right? X equals L. So L cubed, right? 1 PL cubed plus 1/8 PL, and then times L squared, okay? And then plus C3 times L plus C4, okay? Is that right? 1/24, plugged it in, 1/8, positive, plugged it in, C3, plugged it in, and then there's that. There's about 1 million places you can make a simple algebra error here, so be super careful, man. All right, here we go. So this one is going to be, let's just make that into an L cubed. L cubed. And then what? Let's make him into a 24 by multiplying by 3. And 3 minus 1 is 2. So 0 equals 1/12 PL cubed plus C3L plus C4. Okay? Or we could move that over here. We could say C4 is equal to minus 1/12 PL cubed minus C3L, okay? And there is an equation, kind of simplified down, using our boundary conditions for C4, okay? So now I've got 1, 2, 3, I just have 2 equations, don't I? Okay? So we can use these. Let's see if we can solve this now. I think we're almost there. Almost there. Okay? Okay, so I'm going to rewrite these guys over there. Just, again, give us some room here. I'm going to do everything I can to get some more room over here. 1/4 P. That's what that was. Okay, so let's just rewrite this over here. C2 equals 0. C1 equals 1/32. PL squared plus C3. And then finally, C4 is equal to 1/12 PL cubed minus C3L. Okay. Okay, there's everything we've derived so far. So let me erase this and give us a little bit more room. And we're still solving for constants. You got our steps 1 through 5? All right, I'm going to erase that too. Give me some more room up here. Oh, now we can go, man. All right, so what's the only thing we haven't used on our boundary conditions? The only thing we haven't used is this guy. So let's see if we do the same thing. Remember when we set theta 1 equal to theta 2? Let's set y1 equal to y2. So here's y1, there's y2. And when y1 equals y2, what do we know? We know that x is L over 4, okay? And again, the EIs are going to divide out. So here we go. We're going to be left with this. 3/24 P. And then instead of x, I'm going to put L over 4. Okay. So let's just put L over 4. Okay. Oh, and it's cubed. Okay. Plus C1x plus C1x. Do we know what C1 is? right over there. Okay? Plus 1 over 32 PL squared plus C3. This whole equation is going to have C3's in it, okay? That's our number that we're going for here. And all that is times, ooh, be careful, all that's times x, right? So that whole entire C1 there, which was this whole thing, is times x. And again, that C2 is 0, isn't it? He goes to 0, okay? So that's one side, that's the y1 equals, here comes the y2 part, okay? What's left? Minus 1/24 PL over 4 all cubed plus 1/8 P L over 4, this time it's squared, plus C3 plus C3x. Oh, and it's not x, it's L over 4. And then plus C4, which is that, right? So minus minus 1/12 PL cubed minus C3L, okay? So simple. Solve all that and just solve it for 3, man. Simple. Holy cow. Let's expand here, shall we? What is this going to be? That's 64. 64 times 24. Oh my gosh. 64 times 24 is 1536. So this comes into 3 divided by 1536. Make sure my signs are right. Plus. Yeah, that's good. Okay. PL cubed. That's this one. Done. And this one, oh, times x. No, times x times L over 4. Okay. So what's that going to become? Plus 1 divided by 128 P, right? The 128 was from 4 times 32. I'm distributing this that way and then that way, okay? P L squared. Oh, I've got to multiply an L, so that becomes an L cubed. Boy, there's so many opportunities to screw this up. Plus C3L over 4. Okay? I think that's one side done. Okay? Equals minus, oh my goodness. So there's a 64, oh, that's another 1536, isn't it? So minus 1 over 1536 PL cubed. Okay? That's that one. And this guy becomes what? 16. 16 times 8 is 128. So plus 1 over 128 PL. There's an L squared times an L. That's a cube. Okay. Plus C3L over 4. Okay. And then minus 1 over 12 PL cubed minus C3L. Okay. Now if I take this C3 over L, or C3L over 4, and I subtract it on that side, whoop, those two go away, don't they? Okay, that's one easy thing. Let's gather up our PL cubes. What do you say? So we have a, what do we have? We have a 3 over 1536, and we have a, let's make him a 1536. 128, let's see, clear. 1536 divided by 128, 12. Plus 12 over 1536, right? And then put this one over here, whoop, plus 1 over 1536. And then that guy, Same as this guy, right? Move him over here. Oh, I got, that's easy, isn't it? There's a plus there and a plus there. Those go away. Wait a minute. So that means this one went away. So I got that one, and I moved that one to the other side. There he is. And then who else is left? One more right there. And that's what? 1536 divided by a 12. That goes in there. No, I multiplied. 1536 divided by 12 equals 128. So this guy becomes 128 over 1536. And let's move him to the other side. So he's negative. He's going to become a positive. Okay? So plus 128 over 1536. Okay? So that's that guy and that guy. Yes, yes. And that guy, yes. And it only leaves that guy equals negative C3L. So all of that times PL cubed. Sorry, almost missed that. So C3 is equal to, now one of the L's is going to go into there, make him a square. It's going to equal, then we just got to get all that, and it's going to be negative, right? So minus, how many is that? 4 plus 128 is 132 over 1536 times PL squared. Let's see, 132 divided by 11 is 12. Let's see. 132 divided by 12, and then 1536 divided by 12. Okay, here we go. So C3 equals 11 over 128 to the negative PL squared. Oh my gosh, right? Now this is good because C3 now it's just the constant doesn't have any unknowns. It doesn't have any x's. Done, man. We're good. Now what can we do? What does C1 equal, right? What is C1 going to equal? Well, C1, well, let's go up here. Let's erase again. Okay. Let's get C1. Holy cow. There is some algebra here today. Okay. So C1 is equal to 1 over 32 PL squared plus C3, which is that. Or we could just say minus 11 over 128 PL squared. And so let's see, what is that? 128 divided by 32 is 4. 4 over 128. And 4 minus 11 is what? So C1 is equal to minus 7 over 128, right? PL squared. Okay, there's another one. Of course, C2, we remember he's 0. And then we come back, we would like to have C4 as well. Let's get C4. Let's see if that's hard. C4 is equal to minus 1/12 PL cubed minus C3L. Okay, so minus a minus turns him into a plus. 11 over 128 PL squared. That's C3, but then I got to multiply it by L. So times, it's just going to make this, it's going to make this guy into a cube, isn't it? Okay. So we know a common denominator for that is 1536, right? Well, 128 times 12 is 1536. So 12 times 11 is, oh my gosh, 12 times 11, 132. So this comes 132 over 1536 PL cubed plus negative 1/12. And this one in 1536, let's see, 1536 divided by 12, 128. Holy moly, so the whole thing, what? That whole thing is going to boil down to 4 over 1536 PL cubed, which would be, this is for C4, which would be what? 1536 divided by 4 equals 384. 1 over 384 PL cubed. There's my C4 right there, okay? Oh, equals C4. Now I got all my constants, don't I? Okay? So the next step, let's go back to our original equations. Let's plug these things in and let's see if we can find the final answer, which is what in the heck is the deflection at point C? Okay, gang, so what I'm going to do is I'm going to erase all this up here where we found all this stuff. We need C4? We need C4, don't we? We need C4. Okay. And I'm going to rewrite these two and those two one more time up here, and I'm going to substitute in these constants that we just found and write some equations here, okay? So, you want to find the deflection in segment 1? Here's what you need to do. 1 over E times I of 3/24 P x cubed, right? Plus, okay, C1x, so that times x. Well, let's just put a minus there then. Minus 7 over 128 PL squared x plus 0. That equation's done. Good job. Okay? You want to find the slope. For number 1, you got to do this. 1 over EI times 3/8 PX squared plus C1. And what's C1? Just that, right? So minus 7 over 128 PL squared. Done. Okay? Now Y2, okay? Let's do those a little bit lower, okay? So Y2, what does Y2 equal to? Right over there, 1 over E times I, okay? Times negative 1 over 24 PX cubed plus 1/8 PLX squared. I'm moving that again. 1 over 384 PL cubed equals C4. I might need him in a second. But right now, I need this space. Okay. All right, PX squared, there we go. Right there, PLX squared plus C3 times X. Where's C3? Right there. So, let's just make that a minus. Minus 11 over 128 PL squared X, right? C3 times X plus C4. So plus this bit. Plus 1 over 384 PL cubed. All right? Oh my goodness. Okay, and then finally, what? Oh my goodness, what's left? Theta 2 is equal to 1 over E times I of negative 1/8 P, that's a P, X squared plus PLX over 4 plus C3, right? And C3 is that. So minus 11 over 128 PL squared. Close parentheses. Okay, so there it is. You want to calculate the position of anywhere, right? Any x from there to there, you use this equation. I'm sorry, any y rather. Any y from here to here, you use that equation. Any slope on this part of the line over here, use that equation. Any slope on that part of the line, use that equation, okay? So after all that work, all we have done is come up with an equation to find the slope and deflection at point C, okay? So let's erase all of this now. Oh, we're gonna have to, if we messed up, we'll just have to go back and find our spot. But I think everything is good. Okay, here we go. We're almost there, boy. We're almost there. Okay, I mean, really, what's left to do? I'll tell you what's left to do. Now, does it matter if we use, because we're asked to find deflection at point C, right? Now, point C is right here. So does it matter, since point C is right on the line, does it matter if we use section 2 or section 1? The answer is, it doesn't matter. You'll get the exact same answer, okay? Because they're equal to each other, aren't they? So since we know they're equal to each other, we know whether we use this guy to solve for y or that guy to solve for y, we should get the exact same answer, okay? So we'll just use this one up here. And what are we going to do? All we're going to do is what? Where we see an x, what are we going to do? We wanted to find it at point C. So just plug in L over 4. That's all we got to do. Okay? So what is y? What is the deflection at point C? Okay? Deflection, that's y, is equal to 1 over E times I of 3/24 P times L over 4 cubed minus 7 over 128 P L squared times L over 4. Okay? And what is that going to be? Let's see. There we go. 64 times 24 again. Okay, I have the worst memory. 64 times 24, 1536. Okay, so this is going to be 3 over 1536 PL cubed minus, what is 128 times 4? It's 512. So 7 over 512 PL cubed, right? And what's the, oh, it goes in there, doesn't it? That will go into that 3 times, right? 1536, right? 3 times 1536. 3 times is 21. And 3 minus 21 is minus 18, right? So y is equal to 1 over E times I times minus 18 over 1536 PL cubed. And we could probably simplify that, right? That would be, let's see, 1536 divided by 18 is asking for too much, isn't it? Oh, of course it is. 1536 divided by 2, 768. So we could use that. We could say 1 over E times I is equal to, times minus 9 over 768 PL cubed. Okay? And that would be my final answer for the displacement of y. And that may go down a little bit more. Let's see, divided by 3 equals, oh, it does, 3 over 256. There you go. Okay? That doesn't go down anymore, does it? 256 divided by 3. No. Okay. So I think that's it. That's going to be your deflection. at point C. Now one more thing, what is the slope at point C? Okay? I don't know if you're like my students, you hate to work these problems with letters in them, man. Okay, here we go. Let's find the slope. So theta is equal to 1 over E times I of 3/8 P times L over 4 squared minus 7 over 128 P L squared. Okay, which is equal to 16 times 8 is 128, right? So that's going to be 3 over 128 minus 7 over 128, which is minus 4 over 128 times P L squared. And that, my friends, is the slope at point C. We did it. Okay? All of that work, that was way over an hour's worth of work for the answer. And there it is. Okay? So hopefully you can take this technique and apply it to other problems and get these figured out. You'd think, when you look at this, you'd think, well, I can do that problem in 2 minutes, right? It's just a simple one load on a beam. How easy is that going to be? Not very. Okay. I hope all this made sense. I hope you stayed with me, and I hope to see you next time. Thanks for watching, guys.